Hello again, students. Let's keep going on this chapter on rotation. So let's talk about tangential speed. When I was doing the demo outside with the bicycle wheel rotating, I had a post-it note, and that post-it note was definitely moving. And the speed at which it was moving is called the tangential speed. Now, to go with that tangential speed, there is a tangential velocity. The thing is, though, that when the post-it note was, let's say, right here, its velocity vector was like this. But a little while later, the post-it note was, let's say, right there, and its velocity vector had changed. So it's a constantly changing thing. And all right. Now, the speed of the post-it note, the speed of an object on the rim of the wheel, is given by the formula r omega. R, you'll remember, is the radius of the wheel, and omega is the rotational velocity or rotational speed. So let's do a little example here. Let's take a look. And Naughty Peter, I wonder who that was. Naughty Peter is sticking his head out of the car of his dad in the back roads of Maine. And the roads of Maine were mostly dirt and gravel and so on. And once in a while, a stone would get cut in the tread. And you'd hear a click, 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 click sound as the car went along. Okay, so the stone was stuck in a tire, and the wheel's diameter was a half a meter. What was the speed of the stone when it got unstuck and pow, hit Peter in the head? Let's say that the clicking sound was 4 clicks per second. So that means that the stone went around 4 times per second. In other words, the rotational speed of the wheel was 4 revolutions per second. But we're going to need to convert that to radians per second. Now, a few slides back, I said to you that 1 revolution is equal to 2 pi radians. So we can set up the conversion factor this way. Notice that revolutions will now cancel, and we're going to have, after doing the arithmetic, 25.1 radians per second. Now that we've got the rotational speed in the right units, let's use the formula. The formula was right here, r omega, to find the tangential speed. And so we plug in 0.5 meters, 25.1 radians per second, and get our answer, 12.6 meters per second. And yes, that hurts. Now, one thing, here's an example of the radians just disappearing. Notice the radians are no longer in the final answer. So this is going to happen quite a lot when you're doing homework problems. The units of radians will disappear. Okay, now going back to this discussion up here, the fact that the tangential velocity is this way and then this way, that implies that there was an acceleration. And so that's what we're about to talk about. It's called centripetal acceleration. And actually, come to think of it, we've talked about this before. And you've already seen this formula here. If you want to compute the centripetal acceleration, you take the speed, now this is actually the tangential speed, square it and divide by r. And that's our centripetal acceleration. And then if you multiply by the mass of whatever it is, you get the centripetal force. Now, let's do a little bit of algebra. We're going to get a new formula for the centripetal force. So V is equal to R times omega. So you plug that in there. We have the centripetal acceleration is V squared. So now it's R omega, all of that squared over R. and the r's partially cancel, and you end up with r omega squared equals to the centripetal acceleration. Okay, so this is now an important formula. And to go with that, if I multiply by m, I get that the centripetal force is m times r omega squared. All right, so let's have a follow-on example from before. That stone which was stuck in the tire, let's say that it had a mass of 0.02 kilograms. What was the centripetal force that was keeping it stuck, right? So for a long time it wasn't stuck. It was being held on by the friction, I guess, of the tire treads. And so how much friction or how much force was that? The centripetal force, what was that? So we just plug in. We've got the mass of 0.02 kilograms. We've got the radius of the tire, r, and we've got the rotational speed of the wheel, 25.1 radians per second. Don't forget that it is squared, so we want to square that. And we do the math, and we get our answer. Let's see. Now, look at the units. The answer was 6.3. And so we have the kilograms. We have the meters. We have the 1/seconds squared here. And the radians are gone, right? So once again, the radians can just disappear. And I hope this isn't too much of a shock to you, but a kilogram meter per second squared is the same thing as a Newton. All right. So let's go to one more topic here, kinetic energy, right? So you know that if an object with mass m is going at a velocity v, its kinetic energy is 1/2 mv squared. Well, with a little bit of algebra plugging stuff in, we can find that the kinetic energy is 1/2 times I times omega squared. But I didn't tell you what is I, but you're about to find out. I is something that is similar to mass, but it's just for rotations. It's called the moment of inertia. And you need to be able to figure this out. So let's start with an easy one to figure out. What if we have it's not a wheel, it's something, it's going round and round, and it has, so this is the axis of rotation. It's got just a mass right there, and it's out at a radius r from the axis, and it's just going round and round. Okay, so it's got, I guess it has a tangential velocity like this, and an omega. So it's going like this. So it has this whole thing has a rotational speed of omega. Okay, so in this situation, the moment of inertia is mr squared. So the mass times the radius squared, and you can plug that into here. Okay, so let's have an example. All right. So first we're going to figure out the moment of inertia for this example. We have a 1 kilogram mass at the end of a 25 centimeter stick. So basically it's a hammer. What is its moment of inertia? So we put in the mass, 1 kilogram. We put in the radius, 25 centimeters converts to 0.25 meters, and right, it's squared, right? That's our formula. And so we get that the moment of inertia is 0.0625 kilogram meters squared. So okay, so now we've got these funny units here, kilograms for the m part of it, right? And then meters squared for the radius squared part of it. So, okay, so we have a new thing here, moment of inertia with its own units. Okay, but we figured it out. Now we know what the moment of inertia is for this hammer. Now, moving on, we want to know its kinetic energy. And so let's say that it was going around at a rotational speed of 15 radians per second. So let's see. Our kinetic energy formula was this: K equals 1/2 I omega squared. We're going to use it. So we're going to say, okay, K equals 1/2 I omega squared equals 1/2. Now, the I, we've just figured it out, right? It's this number here, so it goes into here. And omega is a given, right? It's the 15. And so here we go, the 15. So it's going to be 15 squared times this divided by 2, and we get our answer, 7 kilogram meters squared per second squared. Once again, the radians have vanished, and this combination of units is the same thing as a joule.